Hi, I'm Terry Ord from the Evolution and Ecology Research Centre at the University of New South Wales in Sydney. Central place foragers are animals that establish some type of central refuge. It could be a nest that, for example, birds invest in constructing and maintaining. It could be a burrow, for example, in the case that we have up on the screen here, wombats, or something like a hive for bees or wasps. Now, there are advantages of adopting this strategy. And obviously, that animal has that refuge that they can return to periodically and shelter from things like predation, but also potentially parasitism, and also environmental variation, day-to-day fluctuations in temperature, for example, or seasonal effects. But it does come at a compromise of mobility. So these animals are essentially rooted in space that actually have a permanent residency. So as they move out from that refuge to forage, for example, they can deplete the resources around the locality to the point that, as we see here up on the screen here, of reef fish who move out from the reef to graze in amongst the seagrass and progressively deplete the resources to produce these really prominent grazing halos around those reefs. But there can also be problems associated with environmental change, for example, severe changes or abrupt changes, things like droughts or floods or perhaps bushfire. These central place foragers tend to be very vulnerable to those environmental changes because they are essentially rooted in space. A classic example of a central place forager is an ant, and in particular, an iconic ant is the Australian meat ant. Now, these ants establish really large, conspicuous nests in the Australian landscape. These nests can be part of a network of as many as 8 nests, and they're massive. Each nest can be, 500,000 workers just inside that one single nest. They are long-lived. They can be decades old. And because they're so large and there's so much investment in the construction of that nest, colony is essentially rooted in place. It's a permanent nest. So these ants are ecologically dominant and really important for the Australian landscape as well. They're widely distributed throughout the whole of southeast eastern Australia. In fact, they cover pretty much a third of the entire Australian continent. And they dominate the invertebrate fauna at these locations, in particular the ant faunas. So these ants will establish these foraging trails on a daily basis. Some of these trails go to trees where the workers are actually harvesting sugars from aphids. But in many cases, those foraging trails just go out into the landscape as these workers are trying to find things like dead insects, but also seeds and also dead lizards, anything that's out there that they can actually scavenge and bring back to the nest and maintain that nest. Now, I've been surveying or monitoring a population of meat ants at my main field site in the New South Wales Central Tablelands. I've got a satellite image up here, and you can see that each of one of those triangles, that's an individual nest. And you can see that they're actually hugging the forest tree line there. And if we return and have a look at that photo, there seems to be this kind of balance between obtaining heat from sun, but not too much heat, and having enough shade to maintain that nest in a thermal window. So this balance of sun and shade seems to matter, and as a consequence, nest location seems to matter. So I was really interested in this idea that if, sun-shade balance matters and subsequently nest location matters, and it really does seem to be the case given that they really are hugging that forest edge tree line, what's the consequences of them getting it wrong? What if a colony puts a nest in a location that is suboptimal or it changes in some way? Can they compensate behaviorally when that nest is not in a particularly ideal situation? So I began by recording the foraging activity along those foraging trails that are branching out from those nests, setting up video cameras for 11 different nests. These are highlighted in the orange. And I recorded foraging activity every hour from dawn to dusk in both winter and summer. And I measured the surface temperature at the time those video recordings were done. And I counted the number of workers going along those foraging trails, and you put all that data together and you can create these statistical curves, or what we call these foraging performance curves, remembering that ants are obviously ectotherms, so temperature does matter. In this particular case, these ants are not leaving the nest until it gets up to about 15 degrees Celsius, and then if it gets too hot, that activity starts to decline, and by 45 degrees Celsius, they're refuging inside that nest. In addition to that, I put out a half dozen data loggers. These are highlighted by those orange arrows. I've got a photograph here of nest 56. This will become important later on in the talk. And you can see the temperature probe that's balanced on top of that nest, taking those hourly temperature measurements over the course of over a year and a half. And I've got two little native Australians there in the background just for scale. So if you marry that foraging performance curve with the hourly temperature on the surface of that nest across that year and a half to a year period, you can actually calculate the number of foraging hours an individual nest can have at different times of the year. And as you'll see from this plot, you can see that in summer, there are periods where it just gets too hot for these animals to be out on the surface of their nest and off foraging. But I want to draw your attention to that winter period. And it seems to be that there are quite a lot of days in the winter where it's just too cold for these ants to actually come out of the nest and forage and maintain that nest. So we can calculate the daily foraging hours for all of those nests over that 1.5 to 2 year period that the data loggers were out there. And if we focus on the 6, you can see that there are extremes. There is one nest, this is nest 11 up in the corner here, that has the most foraging hours on average across the entire couple of years. And down at the bottom here, we have the least, which is that nest 56, least number of foraging hours. So there is variation across those 6 nests, contingent on where those nests are positioned. And as a consequence, the temperature conditions those nests experience has a big impact on the number of foraging hours that those nests actually have to maintain themselves. So if we just zoom in on those 2 extreme nests here, and I want to draw your attention in particular to that winter period again. There's some variation in the summer, but things really distinguish between the nests based on location in the winter. Nest 11 had the most foraging hours over the entire annual period, has on average probably about 6 hours to go out of the nest to forage on an average winter day. Now, in contrast to nest 56, we see that there are many days in winter, this is the same period, that it's just simply too cold because there's too much shade for those ants to actually leave the nest and forage. So there is this difference of the number of foraging capacity as a function of nest location. Now that question, perhaps these ants are capable of compensating behaviorally. So fewer foraging hours might actually be compensated for by more foraging effort. So establishing more foraging trails in those few hours that you actually have to be able to leave the nest. And you would actually predict that as the number of winter foraging hours decreases for a given nest, the colony will actually establish more foraging trails out from that nest. And as a consequence, there's no difference in terms of the nest health. So nest size, the number of entrances is correlated to the number of ants inside the nest. And we really wouldn't expect to see any predictive trend between the number of winter daily foraging hours and nest size, again, as a surrogate for nest health. If we look at the data, though, we find that there isn't any of this compensation. Fewer foraging hours does not equal more foraging effort. There's fewer trails on those nests that have fewer foraging winter hours. Those foraging trails are standardized for nest size. And if we look at the nest size itself, we find that those 2 bottom nests, nest 56 and nest 59, are on average quite small compared to the other 4 nests that were being monitored. Now, if we zoom in on those 2 nests down the bottom here, you can see that over the 8 years that I've been monitoring this population, those 2 nests have been progressively declining. The other 4, the size of the nest has either been increasing or there hasn't really been any predictable change from one year to the next. For these 2 nests, nest 56, where we have the photograph up the top there, that was the one I drew your attention to earlier on in the talk. You can see that there's been this progressive decline over that 8-year period. But it's quite striking for nest 59, where we started out with over 300,000 ants in that nest, to the point that when I surveyed it this year, there was a single entrance hole and probably less than 1,000 ants in that nest. I would predict that by this time next year, that nest is actually going to be extinct. So nest location matters. It impacts the sun-shade balance, and that impacts the capacity of a colony to maintain itself. And what we've discovered at this particular location is if those ants, those colonies get it wrong and put their nest in the wrong location, they are subject to decline in overall size and ultimately extinction. If we extend that out to central place foragers more generally, this is troubling because it means that, in particular with the current climate crisis, where we have events that are more frequent and more severe, things like drought, these animals are going to be less able to be able to disperse to other locations to escape those conditions. So in actual fact, we consider them to be permanently placed in that environment, and if it changes, this can be a problem and it could potentially lead to local extinction. Okay, so I just want to acknowledge my co-author, Katrina, who did all the wonderful stats that I've covered in this talk. I've got a video down the bottom here. This is just actually an ant swarm over one of those nests. This is an anti-predator response to stop things like echidnas burrowing in there and getting their eggs. I'd love to hear from you, so send me an email, or you can always just check out my research page if you want to check out the sorts of things that we're up to.